In experiment number 10, we are synthesizing cyclohexene. This is an alkene, and we are starting with an alcohol. So the alcohol will lose water, and you will get an alkene. So by looking at the alcohol dehydration reaction, let's look at the mechanism of a reaction. So let's have an example. For example, if we have the following alcohol. By definition, with alcohol dehydration, we mentioned that this reaction is driven by the type of alcohol that you start with. So if you start with a secondary or a tertiary alcohol, then your mechanism will be driven by an E1 mechanism. And if you start with a primary alcohol, then the mechanism will be driven by an E2. So it solely depends on what type of alcohol you are starting with. For this example, I am starting with a secondary alcohol. So let's look at the mechanism of the reaction. With dehydration, of course, we said that you are going to be losing the OH. So how are you going to be losing the OH? You need a catalyst in the reaction, and the catalyst is going to be sulfuric acid or any type of acid that generates a weak nucleophile. So H2SO4 is a good acid, H3PO4, which is phosphoric acid, the paratoluene sulfonic acid that we talked about also in the course are good acids. So any acid that generate a weak conjugate base, those are going to be good acids for the dehydration. Do not use HCl, do not use HBr, because HCl would generate a Cl minus, and that is substitution. Cl minus is a good nucleophile. Same thing for HBr. So this is the appropriate acid to use in this type of reaction. If you don't use this acid, you will have no elimination whatsoever. So since this one is a secondary alcohol, it's going to undergo E1 mechanism. Okay, so the first step of this reaction, which is common between E2 and E1, is the protonation of the oxygen. This is the first step. So step number 1, I'm just going to go ahead and protonate. I'm just going to write the sulfuric acid. This is the O, the sulfur, and its Lewis structure in there. Just to show you what hydrogen we are taking out. So we can take any one of those hydrogens. It doesn't matter. I can take this hydrogen here, or I can take this hydrogen there. It doesn't matter. So that is an acid-base reaction. The reaction is going to start from the base, so the acid picking the acidic hydrogen. This is going to leave. And we are going to end up getting a protonation. All what I am doing here is making the OH a better leaving group. Okay, so the OH now is water, and water is a better leaving group. Why it's a better leaving group? Because it is a weaker base. If OH leaves, it's going to leave in the form of an OH minus. That is a strong base, a bad leaving group. Water here is going to leave into H2O. H2O is a weaker base than the OH, so this is why it is a better leaving group. So I do have my water in there. Let's go ahead and create two different alpha hydrogens. So I'm just going to change the reactants a little bit, okay? Two different beta hydrogens, I mean. So once you create the water in there, so we're going to go ahead and say, okay, water is going to leave. And when water leaves now, we are going to create a carbocation. So step number 2 over here, I do have a carbocation. So that is going to be step number 1. That is going to be step number 2. So I know here that carbocation is a secondary carbocation, and I cannot make it tertiary because if the plus charge is here or here, it's going to be the same. So with elimination, I need to look at the carbocation, and I need to look at the adjacent carbons and label the hydrogens on the adjacent carbons. This is the alpha carbon, this is the beta carbon. So I have beta 1 in there where I have beta 1 hydrogen, and then I have another type of carbon, which I'm going to call it a beta 2 carbon, and its hydrogen over here is a beta 2 hydrogen, okay? These are the two hydrogens in there. I'm just going to use only one of them. Now we're going to go ahead and react this with H+, with HSO4- that left from the sulfuric acid. So here I do have the HSO4 minus in there, and that conjugate base is whatever reagent I need in order to perform the elimination. So that base is going to attack every single different beta hydrogen. If I have two beta hydrogens, then it's going to attack them, make two products. If I have one beta hydrogen, it's going to make one product. And if I have three beta hydrogens, it's going to make three products in there. So that base is going to come. This is how it does. It does it. The base is going to come, take the hydrogen and form a double bond. This is for beta 1. So if I take minus the beta 1 hydrogen, then my product is going to look like this. My double bond is going to be over here. And if I, HSO4 minus, if I take the beta 2 hydrogen, then in this case, the base is going to come, it's going to take one of these beta 2 hydrogens and make a double bond. Now notice that the double bond is always towards the side of the carbocation. So you are taking actually the hydrogen on beta 2 and making a double bond that is the closest to the carbocation. Not on this side, on this side over here. So you're going to end up getting your second product in there. Now, which one is the major product? The major product is this because it is the most substituted alkene. So this one is the Zaitsev product because it is the most substituted alkene. We call it the Zaitsev product. Why it's the most substituted alkene? Because if you look at your carbon double bond carbon, this is connected to two carbons in there. So this type of alkene, we call it a disubstituted alkene, versus if you look at this double bond over here and you see that it is connected only to one carbon. So this is going to be a mono-substituted alkene. We said that with the degree of stability of alkenes, the more carbons around the double bond, the more stable is the double bond. So here I have two groups around the double bond, one group around the double bond. So definitely the two groups are major. And the major product, we give it the name the Zaitsev product. The minor product, we give it the name the Huffman product. So this one is going to be the major product. Now in our experiment, we are starting, we want to create or we want to make or synthesize a cyclohexane, right? So if we want to synthesize a cyclohexane, this is going to be our product. We do have to start, it's called alcohol dehydration. So we need to have to start with an alcohol. So we have to start with the cyclohexanol in there. Now, once we start with the cyclohexanol, we need to use a sulfuric acid. Okay. Once we use a sulfuric acid in there, we do have two similar types of hydrogens. So this is going to be my beta hydrogen. This is the same beta. This is a symmetrical alcohol. So only I do have one type of beta hydrogen. Whether the double bond will be here or will be here, it's the same product. So I'm just going to go ahead and consider one type of beta hydrogen. This is going to be the alpha in there. And we're going to do the same steps as I did over here with the synthesis or with the mechanism of the reaction. When you write it, please protonate the oxygen, make it water, allow the water to leave, you create a carbocation. Once you create the carbocation, then the conjugate base of the acid will come, take the hydrogen, form a double bond, in this case, and you are going to end up getting your product. Please write the mechanism of the reaction and don't forget to upload it to this sheet over here. It does have a section all the way down over here where you can upload your file. So back to the reaction, we're going to go ahead and open the experiment in a new window. The experiment is going to open up to the chemicals that we need to choose and the solvent in this case. So we know that we need to start with the cyclohexanol. So I'm just going to go ahead and hit on cyclohexanol. For sure, I don't want to use any of the alcohol or the water. I don't want to use those, but you have to use a solvent. So normally when we don't use polar solvents, we go ahead and use diethyl ether in there. After I use the diethyl ether, I'm just going to bring it because right now I did not put all my ingredients in there. Remember that to do a dehydration reaction, you need an acid. You need an acid to protonate that oxygen to make it water. So now I'm going to choose from here sulfuric acid. So this is going to be my sulfuric acid. So I'm just going to bring it and pour it over here. Okay. So now for the contents of my flask in the live data, what do I have in my flask? I have the cyclohexanol, the diethyl ether, and the sulfuric acid. So let's go ahead and build our reaction setup. We do have the condenser. We're gonna bring the heating mannitol. Guys, the heater over here is a must now because we want to use it for elimination. The reaction happens in presence of heat. Probably I neglect to mention this because once you add the sulfuric acid is going to react with the OH protonated. This is an exothermic reaction. And what's going to speed up the reaction is the heat. So heat is a must in this reaction so that we can go ahead and do the elimination and get our alkene. Whether you draw it as a double bond down there or a double bond here, these are exactly the same because the beta hydrogens are the same. So this is another beta hydrogen in here. So again, the double bond can be either here or here, but heat is a must. So this is why in this type of reaction now, we need to go ahead and do heat. Don't forget your nitrogen gas or else everything is going to blow up in the middle of the experiment. And now this is it. This is what I have in there. I'm going to go ahead and take a TLC and I'm going to save it. Now, because it's an alcohol, you can easily see that your RF value over here, you're going to measure your RF value and you are going to go ahead and put the RF for the starting material, which is this spot there. The RF value here is going to be lower compared to the product. The product is a cyclohexene that is nonpolar. So your product, you're expecting your product to be somewhere up there. Okay, or at least higher RF value than that of your reactants. So we're going to go ahead and start our reaction. When we start our reaction, make sure that you are in the live data and we're just going to go ahead and hit start. We're going to start increasing the temperature or increasing the time, 1 minute at a time. So you can see right now that you started forming your product, but you still have some of your reactants in the flask. We're going to stop the reaction once all our reactant, where's that? This is the reactant. So once all our reactant changes into a product, so I don't want to see cyclohexanol anymore, then I know that I'm going to stop my reaction. So we're going to go ahead and increase this. I'm going to increase it 10 minutes at a time. This is one of the reactions that's going to take some time, so I'm just going to go ahead and do 1 hour. So you can see here, after I do 1 hour, I don't have my reactants anymore, which is the cyclohexanol. I ended up getting the cyclohexene. But see what I did over there? I ended up getting another organic. This is called a byproduct. I don't want it. I just want this. But right now, this is it. Even if I keep going with the reaction, I'm not going to get rid of that because I made it. So to get rid of this, I need to do extraction. So now the reaction is done. I'm just going to go ahead and bring the extraction. This is organic and this is organic. So the only reason or the only way I can get rid of or separate those two is not by extraction, it is by distillation. But the reason here where you need to do extraction because I want to get rid of the sulfuric acid. This is an acid, so I have to throw in some base in there just to neutralize it. So we're going to go ahead and add a base to neutralize it, and now I'm done from the acid. This is the organic layer. The aqueous layer has the acid in it. I don't need it. I just need the organic. So drag the organic layer all the way here and dispose this guy, okay? Now in there, I do have what now? I do have my alkene. This is the product that I want, and I have something here that I don't need. So I'm going to go ahead and do I'm going to do distillation. So this is going to be the distillation setup. I'm going to bring my flask here, and I'm going to bring the distillation setup in there. And there's something which is very important that I don't want you to forget, which is the nitrogen gas. So we're going to do the nitrogen gas in there. If you forget the nitrogen gas in the middle of the distillation, this is going to blow up and you have to start again. Before starting the distillation, this is normally what I do. I go to Google and check the boiling point of the cyclohexene and the boiling point for the byproducts. And the way distillation works is that it separates based on boiling point. So the one that has a lower boiling point, it's going to evaporate, and then you're going to collect it in this flask in here. So if you go ahead and check on Google which one has a lower boiling point, you're going to see that this one has a lower boiling point. So this one is going to distill first. So I'm going to keep raising the temperature. Check on Google what temperature do you need for the cyclohexene to distill. And I'm going to keep raising the temperature until all the cyclohexene from this main flask ends up over here. And then I will be stuck with just the byproduct in there that I don't need. Then I can easily collect that. Okay, so we're going to go ahead. Once you start the reaction, the temperature is going to increase. Now, if you bring your cursor to the thermometer, it's right now 25 degrees. So we're going to go ahead and start the reaction. And for this one, I would increase 1 minute at a time, you guys. So this is 1, 2, 3, 4, and 5. 5 minutes till now. And now we can check the temperature of the reaction. Right now it is 83 degrees. We started, so this is the flask in there. So I can easily see here that I do have my cyclohexane. Look, I have my cyclohexane in there. But in this flask, I still have some of my cyclohexane. I'm not done yet. So I'm not done transferring all the cyclohexane. So I need to increase the temperature a little bit more. And now I look at my flask and there I see like I still have cyclohexane. Okay, here you go. I still have cyclohexane in here. And you keep doing this. And I would really prefer that you do it like 1 minute, or maybe you do it 10 minutes in there, but don't go by an hour. Distillation is not like that. So this is going to be your cyclohexane, still cyclohexane in there. We're not done yet. So we're going to do another 10 minutes. So here, see, another 10 minutes in your flask, you ended up having the byproduct. And then in this flask, you ended up having just the cyclohexane. The temperature over here, it's 243 degrees Celsius. So now I'm just going to bring my cyclohexane here. And this is it. This is my purified now product of the cyclohexane. So now we're going to go ahead and get a TLC for that. And you can see that the RF is going to be higher because it is a nonpolar. After you get the TLC, we're going to save that. Go ahead and get your RF values. And then we're going to do the IR and the proton NMR as we did earlier. So what we're looking for in the cyclohexane, again, please read the spectrum from left to right. We're looking for the functional groups of the cyclohexane. So this is going to be the cyclohexane in there, and we do have the vibration at a higher wave number for the CH stretch, the sp2CH stretch. If we open the IR table in there for the alkene, so the first thing that we're looking for is the vibration of the CH stretch, and it's going to be in this region. That is going to be peak number 1. It is a medium peak. And actually, we do see it over here. So that is the median peak. And then we do have another peak around 1640. Let's go to that same sheet for the alkene, for the C double bond C. So between 1680 and 1640, in our spectrum, it appears at 1640 probably. It's a short peak or median peak. And this is the C double bond C stretch of the alkene. Guys, whenever you are writing the type of the functional group, you can simply write it as an alkene, or you can write it as whatever you have over here, a C double bond C or a double bond CH. Any one of those can do. Now another peak for the alkene is the band, which is between 1,000 and 650. This is the double bond CH band in there. And if you look at another IR sheet or another IR sheet that I posted in here, this is the same thing. So this is the IR band of the C double bond 8, C double bond CH, which is around 910. It falls in this region over here between 1,000 and 650. So if you want to go ahead and look at it in the spectrum between 1,000 and this is a 750 in there. So it is around this here. So it's around here, around like 910. So this is the double bond CH bend, okay, of the alkene. So that is the double bond CH bend of the alkene. So these are the three peaks for the FTIR. Now for the proton NMR. Now for the proton NMR, you can see that we have three different signals in there. This means that we have three different hydrogens. Those two have the same number of hydrogens, and this one has less number of hydrogens. You can see, look and see the intensity of the peak in there. Whenever I see something like this, I mean, this is not a complete singlet in there or one peak, because if you go ahead and you zoom on those peaks, you're gonna see that they are made up of some splitting in there. So this is gonna be maybe like a triplet or So that one might be a triplet or a multiplet. This one might be a multiplet as well. And if I zoom on this one, I mean, this one is not going to be a singlet because I can see how broad it is. So this probably also a triplet as well. And we can verify this. Let's zoom out. We can verify this by simply drawing our structure in there and looking at the structure in its and how many different hydrogens do we have. So if you look at your structure over here, we do have our alkene. We know that alkenes are sp2 carbons, right? And the hydrogens that are connected to the carbon, to the sp2 carbon in here, they are more de-shielded. So I'm expecting the hydrogen that is on this double bond to be further downfield compared to the hydrogens that are away from the double bond. Let's put a split screen in here. Here you go. So I'm expecting that this proton in here to be this one. But how many do I have? I do have these two that are the same. So I'm just going to call both of these proton 1, proton 1. Okay, so proton 1 are the signal over here. And then I have proton 2. So this is hydrogen, hydrogen. Both of those are hydrogen 2s, and these are the same. And these are hydrogen 2s as well. Okay, these are closer to the double bond, so I expect them to be more de-shielded than this signal over here, which is far away from the double bond. And that signal will correspond to 4 hydrogens as well. And I'm going to call this proton 3. Okay, so proton 3, when you do the integration, of course, should correspond to 4 hydrogens. Proton 2 should correspond to 4 hydrogens as well. And proton 1 corresponds to 2 hydrogens. It makes sense because it is its intensity is lower than that of 2 and the 3. We can simply draw a plane of symmetry over here, right? So this hydrogen will be split by the 2 protons into a triplet because it's 2 plus 1. So hydrogen 1 will appear as a triplet. You can see over here, it appears to be a singlet, but in reality, if you just go ahead and zoom in, zoom more, I mean, it should be more splitting pattern in there because take a look, this is not a sharp tip for the peak. So definitely this is more than one peak. And every time you do the splitting, this is the multiplicity, okay? So every time you do the splitting, you look at the neighboring hydrogen. the rule of thumb for splitting is that the neighboring hydrogen should not be far away from the actual hydrogen by more than 3 sigma bonds. So this is 1, this is 2, and this is a 3. So definitely hydrogen 2 is going to split hydrogen 1 into 3 peaks. So it's going to be 3 peaks, but it's going to look high in the integration. It's going to correspond to 2 hydrogens. Same thing for hydrogen 2. So same thing for hydrogen 2 over there. So if I go ahead and do the splitting pattern for hydrogen 2, you can see that hydrogen 2 should be made up of more than 1 peak in there. So hydrogen 2 is going to be split by actually more than 3 peaks. You do have 2 hydrogens on this side and you have 1 hydrogen on this side. So this is a 3 plus 1, so 4. So hydrogen 2 is going to be a quartet. This is the multiplicity for it. Hydrogen 2 is going to correspond to 1, 2, 3, 4 hydrogens. These are the number of hydrogens for the signal for 2. And then hydrogen 3 is going to be split by the neighbor. These are the 2 neighbors in there. This is just a symmetry of hydrogen 3, so it doesn't split it, just increase its intensity. So hydrogen 3 is going to be split by 2 plus 1. So hydrogen 3 is going to be a triplet in there, and hydrogen 3 is going to correspond to 4 signals. And guys, this is lab number 10. If you have any questions, please let me know.